Introduction to solutions. So matter can be broken up into different categories. We tend to break it up into pure substances, of which we have elements, the things on the periodic table, and compounds, combinations of those elements. The other side of pure substances would be mixtures, and for mixtures we break it up into two categories. One we call homogeneous, the other one we call heterogeneous. So far we've been looking at pure substances. Now we're going to start looking at a particular type of mixture. First, we need to be clear on what elements and compounds and atoms and molecules are. Elements can be atoms, things like the noble gases. They can also be molecules, as long as they're made up of the same type of element. Compounds can be molecules, like water. You have hydrogen atoms and oxygen atoms bonded covalently, making them a molecule. But compounds cannot be atoms. Remember, compounds can be molecules. They could also be other things like ionic substances. So looking at mixtures, we have several different types of mixtures which we can fit into one of the two categories of homogeneous or heterogeneous. Suspensions are mixtures where you can actually see the particles that are in them. So because of this, they fit into the heterogeneous category. We can see the different bits that are in there. So for example, if you have little bits of sand in water suspended in there, we call that a heterogeneous mixture, a suspension. If you have orange juice with little bits of orange in there, the pulp in there, you can see the pulp and you can see the orange juice, two different parts to it, so it is also a suspension. Colloids are a type of mixture where the particles are too small to be seen, and therefore they are a homogeneous mixture. Things like milk, if you look at it, you can't see different little particles in there. It all looks the same, so it is homogeneous. You can even get homogeneous milk. And things like paint, same thing. You cannot see the little bits that are in there. They are all, it looks like one thing. There are different particles in there. It is a mixture, but you cannot see the different parts. So that we call a colloid. The third type, the part that we're going to be spending most time on, are a type of mixture called solutions. Colloids, if you leave them for long enough, if you've ever left a bag of milk in the back of your fridge for a month, or you leave a can of paint for a couple of years, the little particles that are in there, they are too small to be seen, but they are big enough that if you give them a long enough time, they will separate. Solutions, on the other hand, the particles that make them up are going to be really, really, really small. So you're definitely not going to be able to see them, and they're going to stay suspended. So they're dissolved in that other substance. So these are definitely going to be homogeneous, and the particles are so small they will also not separate, unlike a colloid. So something like salt in water. You can't see the little bits of salt ions in there. They are in there, but they're too small. It is definitely homogeneous, and it will not separate out. Air is another good example of a homogeneous mixture. Lots of different types of particles that are in there, but you can't tell one type of particle from another. The two parts that make up a solution are going to be the solvent and the solute. Essentially, the solvent is the one that's present in larger quantity, and we think of it as the thing that dissolves the solute. So the solute is what goes into the solvent, and the solvent is going to be present in larger quantities. So if you put instant coffee into water, the water is the solvent, the instant coffee is the solute. The solute is being dissolved into the solvent. 9 times out of 10, water is going to be our solvent. Comparing pure substances to solutions, one, we know that if you are a pure substance, you are always in fixed proportions, and this makes a big difference when we go to do our math for solutions. So pure substances are always going to have fixed proportions. So if you're water, you're always going to have 2 hydrogens and 1 oxygen, and that will never ever change. That's what a pure substance is. Pure substances and solutions, they both look uniform. So they look as if they're made of one thing. But a solution has other things in it. It's just way too small to actually see those other things. They look like they're uniform. They look like they're only one thing. But solutions have something else in them. And because of this, you can vary the concentrations or vary composition of that thing that is dissolved in the solvent. So for example, rubbing alcohol. You can buy rubbing alcohol at some discount place, and maybe it's only 50% rubbing alcohol, which is not the greatest for killing things like bacteria and viruses. What you'd really want is 70% rubbing alcohol. Works apparently better at killing microbes. So because you can vary the concentration of alcohol in the water, it could be 50% or it could be 70%, we know that that's a solution. You can't see the alcohol in the water. They look the same, so they still are homogeneous. They are uniform in appearance. But rubbing alcohol is not a pure substance because it does not have a fixed proportion. You can vary the amount of alcohol to water. Can a solvent act as a solute and vice versa? Yes, you can switch between the two. So for example, ethanol and water, you can combine them in any proportion. You could have 1% ethanol, 99% water, or you could have 99% ethanol and 1% water. You can vary the proportions. They are a solution. So these would classify as miscible liquids, liquids that can be combined in any proportion. Thus, both liquids can be the solute or the solvent, depending on how much you have of one or the other. Things that don't like to mix, we can call immiscible liquids. So something like oil and water, they tend not to want to associate with each other, so they would classify as an immiscible liquid. Now, just because we say that something like oil does not dissolve in water, it's not really true. Our definitions are based on some numbers. So essentially, if you can put a bunch in, like more than a gram, we're talking solids here, if you can put more than a gram in 100 mils, we say, okay, that guy's definitely soluble, whatever it is. So like salt into water, you can put more than 1 gram dissolved into 100 mils, so we refer to it as soluble. If it's somewhere between 0.1 and 1 grams, we say it's slightly soluble. And if you can only get less than 0.1 grams in 100 mils, so not very much, we define it as insoluble. Now, it's not really that none of it goes in, because some of it did. It's just such a small amount. Now, gases, very small masses, so they don't really apply to this definition of soluble, because even if you can get a little bit of gas in, the weight might not be much, but it will have a big effect on the solution. Saturated solutions, a couple definitions here. A saturated solution is when the maximum amount of a solute has been dissolved in the solvent. If you have less than the maximum amount, you can call it an unsaturated solution. You can still put more of the solute in. And a supersaturated solution is when you've got too much in there. It can only be like this for a certain period of time. Eventually it's going to want to let go of some of that solute that has dissolved into the solvent. A couple of ways you can get this to happen is if you heat up the solvent, you can actually get it to take on more of the solute. So you're putting in extra solute into the solution, and then you let it cool down, and the solvent will have too much, and so it'll be supersaturated. And again, you have to heat it up and then cool it down. While it's still heated, it won't be saturated. It would just be, sorry, it won't be supersaturated. It would just be saturated. When it cools down, that's when the solute will want to precipitate out, and the solution would have been supersaturated. Is dissolving a chemical or a physical change? Now, when you take something and you dissolve it, you're not changing the chemical makeup of the substance. And because of this, you don't have a new particle being formed. It is only a physical change, not a chemical change. Dissolving is a physical change. So if you were to take glucose as a solid and you threw it into some water, it would become aqueous. Because it's a molecule, the molecule would not break up. It would stay together, but they would separate from each other, so the crystal would break apart, and you'd have individual molecules of your glucose in your solution, but each molecule would still be glucose. That is not a chemical change. If you had sodium chloride, some people think, oh look, this looks like a chemical reaction, and we've got ions here that are aqueous, which is true. So if you take a bunch of sodium chloride and you put it in the water, you will get ions of sodium and ions of chloride. That's not any different. They're just aqueous. Remember, these guys over here are ions as well. They just happen to be in a crystal lattice structure. They go into solution and become aqueous. They have not changed at all. They're still ions. They're just not beside each other anymore. Now they're floating around in the water, surrounded by water.